So let us denote the eigenfunction of Jz by psi of m, where m is the eigenvalue. So this is what we're assuming. And now, because Jz is Hermitian, m is a real number. So we are interested in finding out the finite dimensional Hilbert space that these operators will act on. So keep that in mind. So now let's take one of our operators, say J minus, and apply it to psi of m, and then ask what is the Jz eigenvalue of this new state. Well, let's just apply our Jz operator, and what we can do then is we can use, say, this permutation relationship and write this as J minus Jz psi of m minus J minus psi of m. Now Jz acting on psi of m is just going to give me m times psi of m. So I have this relationship. But m is nothing but a number, so we can just pull this out. So we can write this as m minus 1 times J minus psi of m. So let me just write this on the left-hand side. So Jz acting on J minus psi of m is equal to m minus 1 J minus psi of m. Now we're going to assume that there is no degeneracy. That means that this state has to be proportional to the state psi m minus 1. That is, J minus acting on psi of m must be proportional to the state psi m minus 1, and let us call the proportionality constant C sub m minus 1. So this is the proportionality constant. All right. So similarly, okay, let's take stock. What have we done here? What we have shown is that J minus acting on psi m lowers the Jz eigenvalue by 1. So similarly, we can show that if we have J plus acting on psi m, we get the state that is proportional to psi m plus 1. And the proportionality constant there is dm plus 1. So because of these relationships, we can have the interpretation that J plus is going to be called the raising operator, because it raises the Jz eigenvalue by 1, and J minus is called the lowering operator because it lowers the Jz eigenvalue by 1. Together, these operators are called ladder operators. All right. So the states that we are dealing with, we are going to assume that they're orthonormal. That is, if I take psi m and take the inner product with psi n, then we get delta, say mn, where delta is the Kronecker delta. So we can now use this to find a relationship between the proportionality constant C and D. So let's compute psi m plus 1, the inner product of psi m plus 1, with J plus acting on psi m. Then we know that J plus acting on psi m is going to give me d times m plus 1. And then we are going to have inside the inner product psi m plus 1 with psi m plus 1. So, but by orthonormality, this thing is just 1. So we are going to have d m plus 1. But on the left-hand side, we can bring the j plus over here, and then what we'll get is that we'll just get j plus dagger psi m plus 1 psi of m. But what is j dagger? J dagger is nothing but j minus acting on psi m plus 1. Then psi m dm plus 1. But j minus acting on this will give me psi m times the proportionality constant, but because it's on this side of the inner product, the proportionality constant will get complex conjugated. So we will have C star of m, and then we'll have psi of m times psi of m is equal to dm plus 1. But of course, this is just 1, so we'll have C star of m is equal to dm plus 1. So this relates the two different constants. So, remember that we are looking for finite dimensional representations. So that means that if I keep applying the, say, j plus operator on psi of m, if I keep on applying it, at some point, for some value of m, and let's call that value, say, L, that it'll just give me 0, because otherwise we will always keep on getting a newer and newer wave functions. And by assumption, our representation is finite dimensional, and therefore that cannot happen. So suppose that we have taken such a vector, that vector on which if we apply j plus, it gets annihilated. Then if I apply, say, jz on this vector, where m is equals to L, then of course the eigenvalue here is L. So now if I take this vector and apply on it, say, j plus and j minus, so I'm just gonna denote this wave function by psi L, and take the inner product with it, with psi L, then what we can do is that we can use this commutation relationship and rewrite this thing at the right-hand side as psi L, say j minus j plus 2 j3 acting on psi L. But then this is going to be psi L j minus j plus acting on psi L plus psi L 2 j3 psi L. And on the right-hand side, remember that psi L is annihilated by j plus. So this thing acting on this will give me 0. And then j3 acting on psi L will just give me L. So I'll get 2 times L. And then I will have 1 from the fact that they're normalized. Now on the left-hand side, what we can do is that we can take this guy over here, and then we can write this as j minus acting on psi L is equal to, and the inner product with j minus acting on psi L. But j minus acting on psi L just gives me C times L minus 1. and J minus acting on psi L, but conjugated gives me C star. So I get this thing squared times 1. So this is going to be the result from my left-hand side. So in other words, what I'm getting is that I'm getting that what I'm getting is that CL minus 1 mod squared is 2L. But remember that C star of L is equal to D L plus 1. So that means we'll get D L squared is 2L, and therefore we can choose the value of DL to be square root of 2L. So this is one of our results. Now, what we did is that we evaluated this commutation relationship for a state which had the highest value of m possible. But what if we did it for an arbitrary state? What if we said, okay, what if I take some arbitrary state psi m, and then I take here the commutator of j plus and j minus, and take another state psi m, and evaluate this inner product. Well, the commutator tells us that on the right hand side, I should get 2 times psi m jz acting on psi m. Or on the right hand side, I should get 2m. And on the left hand side, I'll get, just a little bit of algebra shows that I'll get dm mod squared minus dm plus 1 mod squared. So in the previous case, what happened was that we put L equals to M, and because that L is the highest value that M can take, this term was 0. This term was annihilated by, so this came into play, and that term was annihilated. But in general, this term will not be annihilated. So this is an important relationship. What we've found is that this is what we call a recursion relationship. So if we know the extremal value of one of these constants, we can derive the other values by using this relationship. And of course we do. We know the value of dm is equals to L, which is square root of 2L. So we can now derive any other value of d from this. How do we do this? Okay. So we get that d L minus 1 squared is equal to dl squared plus 2. What is the value of m here? The value of m here is L minus 1. And what is this thing? This thing is simply 2L. So we have 2L plus 2 times L minus 1. So that means I have 2 times 2L minus 1. So from here, we get the value of dl minus 1 squared. Of course, we can take the square root of this. So similarly, we can find that what is the value of dl minus 2 squared? It'll be given in terms of the value of dl minus 1 squared. And then I get 2 times, what is the value of m now? It's L minus 2. So this is going to be 2 times 2L minus 1 plus 2L minus 2. And then we can write this as 2 times, how many L's are there? 2L plus 1L is going to give me 3L. And then I get minus 1 from here, and I'm going to get minus 2 from there. So I'm not going to simplify because there will be a pattern emerging. So we can now do this like S times. So if you go down S times by applying our lowering operator, we are going to get to dl L minus S whole squared, and that's going to give us, we'll have 2, and here we are going to get, here we had 3 times L, and so what we're going to do, so this 3 was related to this guy, so here we're going to have S plus 1 times L, and then I'll get a bunch of numbers, 1 minus 2 minus 3 dot 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 minus S. So then what we can do is that we can write this as 2 times S plus 1 times L, and here this is a arithmetic series, and we can sum that up and we find half times S plus 1, which can be very easily simplified by, well, we can just take the bracket off, then we have 2S plus 1 times L minus S times S plus 1, and then we can factor out S plus 1, and then we have 2L minus S. So this is the general value of D. Now, the thing is that S is a positive integer because it just counts the number of times that we have applied our lowering operator. So S is a positive integer. So now the thing is that we are assuming that our that this Hilbert space is finite dimensional. That means that at some point, as we lower the JZ eigenvalue, that we will come to a halt. So at some point, say J minus acting on some psi is going to give me 0. But that can only happen if at some point in lowering, one of these constants go to 0. But this constant can only go to 0 if this thing goes to 0. In other words, it must be that there must be some value of S, let's call it, say, S prime, for which this is equal to 2L. So that means that the number L, which was the highest number eigenvalue of the JZ operator, can have that the number L is S prime by 2, but S prime is an integer, therefore the allowed values of S are either integer or half integer. So it can be 0, or it can be half, or it can be 1, or it can be 3 halves, and it can be 2, it can be 5 halves, dot, dot, dot. So L cannot have arbitrary value. The highest value of JZ must be an integer, a positive integer, or half of a positive integer. So these are the possible values of L. So this implies that the eigenvalues of JZ are either positive multiples of half or negative multiples of half. So let's summarize. So what we found is that when we applied, say, J plus on say psi of M, we got so let's go. So this was J plus acting on psi of M, and it gave me D M plus 1. And we found what the value of D in general is. The general value of D is given by this. So J plus acting on psi M plus 1 is going to give me L minus M times L plus M plus 1 square root of psi M plus 1. So this is dm plus 1 psi M plus 1. So the way it's going to work is that we are going to have L minus S is equals to M plus 1. Of course, the value of L is fixed. So therefore, what we can do is that we can replace S by L minus M minus 1. So therefore, I'll have L, therefore I'll have L minus M minus 1 plus 1. That's one term. The other term is going to give me 2L minus L plus M plus 1. So here, these ones cancel out. And over here, I'm going to get 2L and minus L is going to give me just L. And then I'll get plus M plus 1 times I'm going to get L minus M. So using this, we find this lovely relationship. So similarly, by using the value of C, which is related to D, we find that J minus acting on psi M gives me square root of L minus M plus 1 times L plus M psi of M minus 1. So now from this relationship, we can see that when M takes the value of minus L minus 1, we get D star of M or D of M equals to 0. That is when the lowering operator annihilates the state. So let's just let's review, let's summarize what we have learned. What we have learned is that the Jz eigenvalue M can take values from L to plus L. So that means it can take 2L plus 1 values. So the way it works is that suppose we have a state whose eigenvalue, Jz eigenvalue is L. Now if I apply to it a raising operator, say J plus, then it gets annihilated. But if I apply to it a lowering operator, J minus, I get to the state psi L minus 1. But if I'm at state psi L minus 1, if I apply the raising operator, I get to psi L. So if I apply another lowering operator to psi L minus 1, I get psi L minus 2. And I could have gone the other way by applying J plus. And so if I keep applying this raising and lowering operator, I go down what looks like a ladder. And and at some point on the ladder, I will hit a state whose Jz eigenvalue will be minus L plus 1. And then if I do, again, lower it a little bit more, one more, then I get psi of L. And if I do one more, I get minus. And on this side, we get, right, so we get J plus. So this is the picture we have. And these are the 2S plus, these are the two L plus 1 states.